This video I've titled Radio Propagation 101. It will give you a basic understanding of radio propagation. As ham radio operators, we've all seen propagation reports like this. But what do they really mean? High-frequency radio propagation depends on many factors. To begin to understand it, we need to know about the ionosphere and how current solar conditions affect it. The sun not only makes life possible on Earth, it makes long-distance radio propagation possible too. Solar radiation does interesting things to the upper regions of the atmosphere. Dark regions on the solar surface, or sunspots, are responsible for increased magnetic radiation from the sun. This radiation is what gives the ionosphere its ions, which refracts certain radio waves and absorbs others. Sunspots can vary from day to day, but they also tend to follow an 11-year cycle of activity. During peaks in the sunspot number, even very low-power stations can often be heard around the world. Sunspot numbers can also vary on a 27-day cycle due to the rotation of the sun. Of course, the tilting of the Earth on its axis affects propagation too, as well as the time of day. As a very general rule of thumb, frequencies above 10 MHz are useful during the day and below that are good at night. Predicting the actual usable frequency is an art and a science and depends on many factors. Another thing that affects propagation are solar flares, which eject massive amounts of potential and electromagnetic energy over a very wide spectrum. Flares occur near sunspots and often last only a minute or two. Flares are classified by the amount of X-rays that they produce. The biggest flares are X-class flares. M-class flares have a tenth of the energy of an X-class flare, and C-class flares have a tenth of the energy of an M-class flare. Though often short in duration, the effects they have on the ionosphere and radio communications can last for days. The ionosphere refracts radio waves of specific frequencies, primarily high frequencies, 3 to 30 MHz. It is this refraction of radio energy that makes worldwide radio communications possible without the aid of a satellite. There are three basic layers in the ionosphere. The D layer is responsible for absorbing radio frequencies, not refracting. The more the D layer is ionized, the more it absorbs radio energy. Frequencies above 10 MHz are not readily absorbed by the D layer, but lower bands are usually unusable for long-distance communications during the daytime, thanks to the D layer. Like the D layer, the E layer dissipates its energy quickly when the sun is not shining, and therefore is only a major factor during the day. However, unlike the D layer, which absorbs the lower HF spectrum and lets higher frequencies pass through it, the E layer can refract radio signals, cause them to skip back to Earth. At night, when the E layer is very weak, radio signals tend to pass right through it. F1 and F2 are jointly called the F region. In fact, they combine into one F layer at night. The F region is the most important for long-distance HF radio communications. It retains its ions longer than any other layer and remains ionized all night, although not as densely. Its intense daytime ionization refracts high frequencies, but at night will often let them pass through. Low frequencies below 10 to 15 MHz are refracted back to Earth at night. At night, the D layer disappears and the E layer becomes very weak since it can't stay ionized very long. Also, F1 and F2 combine to create a single layer. Low frequencies are now useful since the D layer is no longer there to absorb them. This is why you hear AM radio stations from all over the country at night. The same higher frequencies that are useful during the day may pass right through these less strong night side F regions. The highest frequency that will be refracted by the F region is the maximum usable frequency. It is often a good idea to use a wavelength close to the maximum usable frequency, but lower frequencies may be more prone to absorption and get degraded. Sometimes the maximum usable frequency drops below 5 MHz, or so due to the disturbance or weakened F region. Solar flares can cause such disturbances. Low points on the sunspot cycle don't help either. Current conditions in the atmosphere will greatly affect how radio signals of different frequencies will propagate. Sunspots help increase the atmosphere's ability to refract HF radio waves, while flares can cause disturbances in the ionosphere, known as geometric storms. A disturbance in the ionosphere will do more to absorb HF radio signals than propagate them. Higher sunspot numbers indicate increased ionizing radiation from the sun, which enhances the ionosphere's ability to refract HF signals. The sunspot number can vary from 0 to over 200 during the peak of the 11-year solar cycle. Similar to the sunspot number, the solar flux value is actually a measurement of radio signal from the sun. This index, taken once a day at a frequency of 2800 MHz, increased radio noise from the sun means more ionizing radiation and correlates with the sunspot number. Solar flux values range from 60 to 300. The K index is a code that relates to the maximum fluctuation of horizontal components observed on a magnetometer relative to a quiet day during a 3-hour interval. The conversion table for maximum fluctuation K-index varies from observatory to observatory in such a way that the historical rate of occurrence of certain levels of K are about the same at all observatories. In practice, this means that observatories at higher geomagnetic latitudes require higher levels of fluctuation for a given K-index. There is a relationship between K and A. The A index was invented because there was a need to derive some kind of daily average level of geomagnetic activity. Because of the nonlinear relationship of the K scale to magnetometer fluctuation, it is not meaningful to take an average of a set of K indexes. What is done instead is to convert each K back into a linear scale called an equivalent hourly range A index. The daily A index is merely an average of 8 A indexes. Now here's some math. If we take the K indexes for the day, the daily A index is the average of the equivalent amplitudes. For example, 3 is equal to 15, 4 is equal to 27, 6 is equal to 80, 5 is equal to 48, and so on. So we take these numbers and we add them together. Divide by 8, we end up with 25.25, which gives us our A index for the day. Now that you have a basic understanding of how space weather works, the website I like to go to is Space Weather Prediction Center at www.swpc.noaa.gov. Good DXing! And 73s from N9 LVS.